In this video, we're going to cover how to do a Bohr model. Now, in order to do a Bohr model, you're going to have to remember how to calculate protons, electrons, and neutrons. And you're going to have to remember how to do electron configuration, which were in a previous video to this one. But we will review that a little bit before we go into drawing a Bohr model. And Bohr models are going to be used for all types of bonding, periodic table trends, and just other advanced chemistry concepts. So understanding a Bohr model and how the atom is structured, super important for the other parts of chemistry. So let's get right into it. Let's start out with the calculation of protons, electrons, and neutrons. The atomic number always tells you the number of protons, and the identity of the element is based on the number of protons. So there's 20 protons, it has to be calcium, and if it's calcium, there has to be 20 protons. Okay. Now, the electrons are figured out based on the protons, okay, and the charge. Since there's nothing in the upper right-hand corner, there's no charge. So the protons, which are positive, and the electrons that are negative, they have to match if there's no charge. So we're going to have 20 of each, okay? Now, the neutrons, okay, they have no charge, so I'm not really looking at charge, but I am looking at the mass. The mass is 40, and the mass is going to come from protons and neutrons. So when I add the protons and neutrons together, it needs to equal 40. So 20 plus what number will give me 20? It's going to be 20 as well. So in the calcium atom, there's 20 protons, 20 electrons, and 20 neutrons. Doesn't always work out to be an even number for all of them, so you have to kind of go through that process that I just covered. Now, electron configuration, okay, we're going to use the periodic table, and when we go through the first row, it's going to give us 1s2. When we go through the second row, it's going to be 2s2, 2p6. And if I look at calcium's actually in the fourth row, so I have to go through the whole third row as well. And when I go through the third row, it's going to be 3s2, 3p6, and then I'm only going to go through part of that fourth row to get to calcium, which is going to be 4s2. Now, I know that's really not a description of how to do this. If you want further details on that, you're going to have to watch the video labeled electron configuration. So after we have the electron configuration and we've calculated the protons, electrons, and neutrons, it's very easy to put together a Bohr model. Okay? We are going to draw a little dot that's going to represent the nucleus, and the only thing that's in the nucleus are going to be these protons and neutrons. So I'm just going to draw a label to say, hey, there's 20 protons and 20 neutrons in that tiny little place, okay? And that nucleus has all the mass and occupies a very small space. So this nucleus is very, very extremely dense, okay? Now, the electrons are going to be in orbits in a Bohr model, okay? And the number of rings is actually displayed here in the electron configuration. So this code of electron configuration, okay, it's really easy to figure out. Just got to watch that video. But after you have it figured out, it's very easy to decipher. Sorry about that. So these big numbers, they tell you what ring the electrons are on. The exponents, that tells you how many electrons are on that ring. So the only thing that has the big number 1 in front of it is the 1s2. So I look at the exponent. That tells me that there's going to be 2 electrons on the first ring. Okay. The way you figure out the second ring is I'm going to just box in everything that has a big 2. This is saying, hey, these things are on the second ring. There's 2 electrons here and 6 electrons here. So that means that there's going to be 8 electrons on the second ring. Okay. The third ring is going to be the 3s and the 3p. And once again, 2 plus 6 is going to be 8. And then the fourth ring only has 2. So it's going to look something like this. So our Bohr model has protons and neutrons in the center. Okay. Our electron configuration gives us rings of 2, 8, 8, and 2. Okay. So that's just one example of how to do a Bohr model. Okay. Now, from this Bohr model, sometimes we like to talk about like how we use it to figure other things out. For example, what charge does calcium like to make when it is inside a compound? When it's by itself, it's neutral, but when it's inside a compound, it's typically going to lose electrons or gain electrons according to something that we call the octet rule. And the octet rule is simply 8 is great like chocolate cake. That's a little saying that I have for the octet rule to help you remember it. So 8 is great like chocolate cake. I know it doesn't rhyme, but it does make sense. Okay, so basically what this means is that we're going to take a look at the outermost ring. Okay, and the outermost ring, we call these guys the valence electrons. These other electrons that are not on the outside are called core electrons. And basically the octet rule is saying, hey, if I'm going to end up charging this, I want to have that last ring to be 8. Okay, I want to have 8 valence electrons. So we say in chemistry, as chemistry teachers, that the elements like to have 8 electrons, but at the end of the day, these atoms don't have feelings. Okay, we just personify atoms to make learning chemistry easier. Okay, as you go through this series of chemistry videos that I'm putting out there, we're going to talk more about why they tend to like 8 electrons, but there's some scientific principles that are beyond the scope of this video. So right now, just in the beginning of the year, we're just going to roll with, hey, the atoms, they like to have 8 valence electrons. And the way they can do that is they can adjust by either gaining 1, 2, or 3 electrons or subtracting 1, 2, or 3 electrons. Those are the common things. Now, they could do a little bit more, but the more you add or subtract, the more complicated things become with the atom. Okay, you get a big imbalance of protons and electrons, and that tends not to happen. But losing 1, 2, or 3, or gaining 1, 2, or 3, that's fairly common. So to get up to 8, this thing would have to gain 6. That's a lot of electrons. Okay, it might be easier just to lose these 2 electrons. Okay, now those electrons, they're going to go someplace. They're not just going to go poof and be gone. They're going to go to another atom that actually likes to gain electrons so that they can have 8 on their outermost ring or their valence electrons. So realize that they are going to end up going someplace. But in this case, if we lose the 2 electrons, you're going to see that we're going to get this new layer of 8, okay? And all of a sudden, that last ring is right here now, and those are now the valence electrons. And that happened because 2 electrons were subtracted. They went someplace. So if we come back here and we look at our beginning material, there's no longer 20 electrons, there's 18. And if you have 20 positive particles and 18 negative particles, okay, you're going to end up getting a charge of positive 2. Okay, and positive 2 fits kind of like our scheme that we have for those atoms that are in group 2. Group 2 have 2 valence electrons. They tend to lose those 2 electrons, and when they lose those 2 electrons, they will take on a positive 2 charge. Now remember, that only happens when they're inside compounds. When they are by themselves, they are neutral. Okay, so last thing that we have to adjust is the electron configuration. If we lost 2 electrons, those electrons are no longer there. And you might say, hey, this is the same electron configuration of argon. So we're going to say that argon, which has 18 electrons, and the calcium positive 2 ion, we tend to say that they are isoelectronic. And if something is isoelectronic, that means that they have the same number of electrons. So this prefix iso means the same, kind of like in an isosceles triangle, has 2 sides that are the same. Okay, isoelectronic means that we have the same number of electrons. Okay, so when you form these ions, okay, because they're gaining and losing electrons, they're going to get an electron configuration of another element. Okay, And that other element tends to be all the way to the right on the periodic table under the column of noble gases. Okay, that's typically what's going to happen. Okay, so let's kind of try another one. Okay, so let me erase all this. Let's do a fluorine atom first, and then we'll adjust it and apply the octet rule to it. So the first thing I'm going to do is calculate the protons, electrons, and neutrons. 9, no charge, 9, mass of 19, 10, because 9 plus 10 is 19. Electron configuration is 1s2, 2s2, 2p5, okay? And like I said, if you want more information on how to get this code, watch the video on electron configuration. Making the atom, here's the nucleus. We're going to label the protons and the neutrons because that's what's inside the nucleus. And then the electrons are going to be in rings. And we only have 2 rings. We've got the 1 and the 2. On the first ring, there's only 2 electrons. On the second ring, there's going to be 2 plus 5. So that's going to be 7 electrons. So it's 2 and 7 for the number of electrons on these rings. This guy is going to have 7 valence electrons. And it has 7 valence electrons, and we're trying to apply the octet rule, which is 8 is great like chocolate cake. Okay, this guy's not going to lose all 7. Okay, it's going to actually gain 1 electron. That electron is going to come from someplace, maybe something like calcium that likes to give up 2. Okay, and maybe one of them will go to this fluorine, and maybe the other one will go to another fluorine. So the formula between calcium fluoride would be CaF2, because if calcium's giving up 2, okay, you'd need 2 fluorines because the fluorines only want to gain 1. So if we gain 1 electron, we will get that 8 is great like chocolate cake valence electron ring, okay, which we know this thing's going to be a little bit stable now because it has that noble gas electron configuration, but there's some things that we need to adjust. If we gain 1 electron, instead of having 9 total electrons, there is 10. And if we have 10 negative particles and only 9 positive particles, this thing's going to have a charge of -1. Okay? We need to adjust the electron configuration because of the gaining of the electron. It's no longer 1s2, 2s2, 2p5. It's now going to be 2p6. Okay? And the element that has this electron configuration is going to be neon. So neon and the fluorine that has a -1 charge are going to be isoelectronic. Couple more vocabulary words. Okay, when something does become charged, we call that an ion. So an ion is a charged atom. Okay, and there's 2 types of ions that you can have. You can have something that is a cation, which means it's a positive ion, kind of like the calcium was, because it lost the electrons. It became a positive charge. So calcium would be a cation when it becomes charged. And then we also have the vocabulary word anion, which stands for negative ion. So the fluorine -1 ion would be classified as an anion because it's negative. Okay, and a little mnemonic to help you out. There's a T in cation, which kind of looks like a plus sign. So the cations are the ones that are positive. Okay? And then the last thing I want to talk about is I'm going to come back and do one more problem. I'm going to do magnesium. And I'm going to do magnesium 24. And it has an atomic number of 12. And if I was to calculate its protons, electrons, and neutrons, we would have 12 of each. But there are other forms of magnesium, like maybe magnesium 25. And if I was calculating its protons, electrons, and neutrons, we'd have 12 protons, no charge, so 12 electrons. But the neutrons would now be 13, because 12 plus 13 would be equal to 25. Okay? So what we're trying to say here is that there's different types of magnesiums. Okay? We got magnesium 24 here. We have magnesium 25 here, And the average on the periodic table, if you look it up, says that it's 24.3. And what that means is that it's not equally weighted between magnesium 24 and 25. Okay, it looks like there's going to be a lot more 24s than 25s because the average is a little bit more closer to 24 than it is 25. Okay, and how we calculate this average is for another lesson when we talk about weighted averages and mass spectrometry. Okay, but for today's lesson, we want to recognize that some of these magnesiums are not the same, and there's a vocabulary word that goes for that as well. Okay, and that's called isotopes. Right now, we get that iso prefix again, and that means it's the same element. Okay, but they have different masses, and the reason why they have different masses is because the neutrons are different. Okay, so I hope that helped. Okay, I hope you understand how we put together these Bohr models. Okay, as far as the nucleus and the rings, and using the electron configuration to tell us that. A couple vocabulary words like isoelectronic, anion and cation, the word ion, and isotope. And that kind of concludes the lesson on Bohr models.